Hey guys, what's up? I'm back with day 84. We're going to take a look at some shortcuts here to finding these area bounded region problems. Um, I find these shortcuts especially helpful on the no calculator version of these questions. But again, shortcuts, if they were easy, it would just be called the way, right? So these shortcuts you need to use carefully. You need to make sure that you can use them to help you solve the problem. So let's take a look at a scenario here. I want to find the area of the region bounded by y equals negative x squared plus 4. And the other function is y equals negative 4. I'm going to sketch these in different colors just so we can get an idea of the two different functions. So again, I want the area of that region. So if we take a look at a graph, we know that negative x squared plus 4, that's a downward facing parabola that goes through 1, 2, 3, 4. So it looks something like this. And then, oops, sorry, I should have done that in blue. Okay. So that's that function. In green, we have y equals negative 5. Okay, so what we want to do here is want to find the area of the region bounded by this. So again, we're looking for this area. Okay, so what I want to do is I want to find those two intersection points. So I'm going to set negative x squared plus 4 equal to negative 5. And solving this, I end up with x squared equals 9, and I get x equals plus or minus 3. So these two intersections here, this is at x equals 3, this is at x equals negative 3. Well, when I look at this, now you're certainly welcome to continue this the way we have before. I can do the integral from left to right of top minus bottom. I'm just going to go ahead and solve this quick, and then I'm going to show you the shortcut that might be helpful here. So I want to do the integral from negative 3, the left bound of the region, the x left bound of the region, to the right bound, positive 3, of the top function, which is negative x squared plus 4, minus the bottom function, which is minus negative 5. When we set this up, we need to be very careful with signs here. We always do top function minus bottom function. If it helps, you can put both the top and the bottom function in there. But the bottom function is the one that really absolutely has to be in parentheses to make sure that, especially if the bottom function is a binomial. Now here the bottom function is simply negative 5. So if you forgot the parentheses, it's not the end of the world. But it is a big deal if that bottom function is a binomial. You're going to have to distribute that minus. Now, again, I can go and start doing my definite integral now, but that is not smart. What we want to do is we want to clean up this thing to get it as simple as possible before we do the definite integral. Okay? I know that this is going to change to plus, and this is going to be negative x squared plus 9. That way I don't have both a 4x and a 5x floating around. It just makes it much more simple to solve the problem. So here's what I end up with. Solving this thing out. Oops. I don't need that anymore. It's already simplified. So I'll go straight to the brackets, and I'll have a negative 1/3 x cubed plus 9x. Make sure you do a good antiderivative. Now I have to plug in 3 and negative 3 and subtract these things. So I end up with this. Negative 1/3 3 cubed plus 9 times 3 minus negative 1/3 negative 3 cubed plus 9 times negative 3. Okay? I like to work each one down and then subtract them at the end. 3 cubed is 27. 27 times negative 1/3, right, would be negative 9. So here I get negative 9 plus 27. Over here, negative 3 cubed is negative 27. Negative 27 divided by negative 3 is positive 9 minus 27. If you're doing this, these should look the same, just opposite signs. Negative 9 plus 27 is 18, minus 9 minus 27 is negative 18. Negative 8, or 18 minus negative 18, this becomes plus, and I get 36. Now that wasn't too bad, simply because the numbers worked out to be whole numbers, which was kind of nice. But here's what I want you to look at to make this a little bit easier. These two shaded pieces, right? This blue function here is symmetrical about the y-axis. So what my thought is that this blue region right here, that blue region and this green region if that function is symmetrical, then the blue region and the green region should be identical. So all I have to do is find the area of either the blue or the green, my choice, and double it to get the answer. Now the reason that this becomes easier is because think about writing this integral here. I was going to integrate the blue region. I'm going to use the blue marker. I was going to integrate the blue region. That would just be the integral from 0 to 3 of top function, which is negative x squared plus 4 minus bottom. Okay? But that blue region isn't my final answer. I'm going to have to double that to get my answer. Now the reason I do this is because it's much easier to do definite integrals when we have zeros as one of our limits of integration. So let's see what happens if we do this. Well, here's what we get. We'll clean it up again. I still want to clean this thing up to negative x squared plus 9. And again, if I'm going to take the shortcut, you got to remember to keep writing that 2 over and over again. And again, I get negative 1/3 x cubed plus 9x. Everything should look pretty much the same here, except my limits of integration are different, and I have that 2 out front. So now I get 2 times negative 1/3 of 3 cubed plus 9 times 3. The nice thing is that it's just minus 0 for the second part, right? So solving this thing out here, 3 cubed is 27, so I still end up with negative 9 plus 27. And that's 18, and 2 times 18 is 36. It just makes life a little bit easier. You could have done a similar shortcut on problem 1 of your homework last night. Okay? My calculator isn't working through my screen. I wanted to show you one that was with a calculator. But let me show you 2 more examples of what I'm talking about. So, one of the problems that we had on our homework was this. We had x cubed, which looks like this. And then we had y equals x that looks like this. We should have found these intersection points to be negative 1, 0, and 1. And we had to find the 2 regions, right? We had to find this blue, and we had to find this blue. When we look at it, x cubed is an odd function, and it looks like those 2 areas are the same, right? We could have solved this simply by doing the integral from 0 to 1 of x minus x cubed dx. that will give me this area right here, and I can just double it to get this area right here. And that only works because of the symmetry that we have on here. If you do that integral, you get 1/4. 2 times 1/4 is a half. The answer to this question is a half, right? But we can get there just a little bit quicker doing that. One more thing. I showed you guys this quickly in class, but I just wanted to get it down. One more little shortcut that you can do. It doesn't involve symmetry, but it does involve absolute values. So here are my two functions. This is f. This is g. Now when I look at it, these two areas are clearly not the same. This area is much bigger than this little guy over here. Okay? So one way we could solve this, right? We could find this intersection that I'll call A. Again, I had an example with some real numbers, but my calculator is not working. We'll call this intersection at x equals b, and we'll call this one at x equals c. Now I can solve this in two ways. Now remember, blue here is f, green is g. So I could find this area by doing the integral from a to b, right, of f of x minus g of x dx. So that'll give me the area of this region, making sure that f is on top, so I have to do f minus g, plus the integral from b to c, and now it's g of x minus f of x. And if I add those two up, that'll give me the total area of the bounded region there. But there's another way to do this one too that eliminates needing to know about point B. Okay? So what I can do is, like, imagine, what if I had these backwards here? What if I did for this first integral, if I did g of x minus f of x? Well, that's going to give me a negative answer. And I know that it would just be the positive answer of that. Same with the other region. If I mixed them up, it would just give me a negative number rather than a positive number. Well, if we could just make it so when we subtract them, it always gives us, it just always makes it positive. Then we do the integral, then this thing would work. So you could replace this whole thing with the integral from a to c, a all the way to c, of the absolute value of f of x minus g of x dx. The absolute values must be inside of the integral here. And I can do f of x minus g of x, or I could do g of x minus f of x. Because it doesn't matter the order that I do them in, I just need to subtract them and just make it positive. Okay? Now, this seems like, hey, that's kind of a nice shortcut for the calculator section. Well, yes and no. It's not so much a shortcut as, it's not as big of a shortcut as it looks, because it takes your calculator a long time to spit out an answer when you do the integral of an absolute value. So the time you save in typing it in, oftentimes is kind of negated by the fact that it just takes a while for your calculator to spit out the answer. But those two things, these two things would both give the combined areas of the shaded region there. Just an interesting thing to look at there. That's it for today. Talk to you guys later. 2 chains, bye.